Thanks for attending. And the title of the presentation is Solving the Network Puzzle. So I don't know about you, but I hear a lot of acronyms and initialisms, and it's really confusing, hard to figure out what it's all about. You know, IoT, SDN, NFV, BYOD, DSP, CPU. There's really no end to this list of acronyms. But if we step back and look at the broader picture, it becomes a lot less confusing if we think about how they fit together and which of these technologies form a core that become a basis upon which the others can build upon and interlink with each other. So again, hi, my name is Joe Byrne, and I am our strategy lead in digital networking. And so these core technologies are what I call the evolved network. And an objective of this evolved network of these core technologies and a lot of what's going on today is how do we make the network consumable? Now that's kind of an odd term, odd idea, consumable, but it draws on this idea of what we've seen in the compute space recently in the last 10 years, which is really typified by some cloud service providers where you can offer up a computing resource, and then as a customer needs more of it, you can expand this resource kind of elasticity and compress it down. And this doesn't really exist in networking today. Networking is very much, here's a box, here's what it does, boom, oh, you need more, buy another box, you should have bought a bigger one, slot in another card. So things aren't really as readily consumed. Things are very much fixed and well-defined. So these three core technologies in the evolved network are software-defined networking, and two objectives of SDN are to simplify and improve network configuration and to accelerate the rollout of networking applications. Two, we have network functions virtualization. So this improves elasticity. That goes back to that notion I was talking about kind of scaling up and down depending on the load presented and the needs of the user, of the operator, of the enterprise, and to reduce the cost of network services. And then finally is redistributing intelligence. And this is not really an acronym, but it came about as I was sitting down thinking, what are really the core technologies that a lot of these other ones draw upon? And I came to this idea of redistributed intelligence. And it's different from centralization or decentralization because intelligence can move either direction under this new paradigm. And we'll talk about all of these a little bit further, but the real idea here is to reduce network infrastructure cost, enable these new applications, and improve performance. So what is SDN? SDN defines a platform for network applications. And in my mind, this is really the key figure that explains what SDN is to me, and it provides a framework for understanding it, much as the OSI 7-layer model provided a framework for understanding networks. This is a different framework, taking a different view on how networks can be deployed. So how do we improve configurability and improve feature velocity? Kind of a fancy marketing-ish way of saying implement new features and roll them out quicker and quicker. So first, we make the network programmable, meaning under software control, we can change the behavior of the network. And we do that by centralizing control. So previously, control was adjacent to the data plane, and now we're talking about centralizing it. But then developers need access to the network. So you provide an interface from applications to this controller that can then give commands down to the data plane and tell it how to operate. So a variety of use cases here. simplify provisioning. Let me just zoom in on that one as an example. Let's say we want to have a Lync meeting, Microsoft Lync within our office. We're going to be using the voice features and the video features. We have this big campus here. Today the way the network works is just the data goes out on the network and on a best efforts basis finds its way to the other party or other parties. Well, with SDN, conceivably, the Lync server could say, hey, I'm setting up a connection between these users. They're using the telephony feature. Please take any network traffic that matches this description and give it the highest priority amongst these. And then the network controller can find the optimal route that has the appropriate bandwidth and then apply the QoS rules accordingly. And then service creation insertion. Let's say we want to insert some kind of function, maybe some kind of security function between two nodes. Well, we can use this SDN controller to set up a path such that the traffic from A to B goes through this node that inspects the traffic, for example. NFV decouples applications from hardware. We often hear NFV and SDN talk together, but they're very different things, but they work well together. I like to use the example of peanut butter cups. Peanut butter and chocolate are totally different things, but they taste great together. And key things here are objectives of how do we improve cost and the speed of the applications. And really, again, by speed, we really mean this feature velocity concept again. So we move functions from hardware into software, and then we run those software functions on more general hardware, on multi-core processors. So we've gone from a bespoke system designed to solve a single problem to a more general system based on a multi-core processor that can solve a lot of different problems. And a couple good example cases are aspects of the mobile core network and broadband remote access servers. So functions that tend to rely a lot on the CPU versus things that need a lot of physical ports or things that have a lot of real-time requirements. Those tend to virtualize less well than applications that are more compute related. And then redistributed intelligence, I gave a hint of this earlier. The intelligence, there's a given paradigm today, and we're moving to a paradigm where depending on the particular use case and particular application, the intelligence moves somewhere else in the network. So for example, under SDN control, we talk about centralizing control. Control is essentially intelligence. And so we take some intelligence out of the local node and move it to a central node. Now, it happens to still be local. We're not talking about moving control of your LAN across the country necessarily, but we are moving and centralizing it. Another example would be moving some aspect of the intelligence into the cloud. So there's this idea of virtual customer premises equipment. Customer premises equipment are those boxes that you have in your enterprise that, say, for example, may talk to the service provider and help deliver the network services he delivers. There are certain aspects of these things that can be put in the cloud or controlled from the cloud and centralized there so that when you do the upgrade, you're just upgrading the cloud once, and then the cloud can manage how those are then kind of pushed down and implemented at the lower level. And then the reverse is how do we distribute intelligence, say, from the cloud out to different parts of the network, the metro edge, the access network, or premises. And a classic example here is caching. So today, if you visit a website, mentally you think you're going out to the website's actual server, but a lot of times, a lot of the data isn't being served directly from that, but rather from a cache located nearby. And you do this in cases where you may have like high latency sensitivity, so you need to have a quicker response. Doing this, what I mean is redistributing intelligence down, or if your backhaul required is spans is a big area, but you want to minimize the amount of backhaul. So essentially, instead of sending all the traffic all the way up and all the way down, you just deliver it locally. So hopefully I've shown a little bit about these three technologies, and we could put them together and form this base layer that I call the evolved network. And then we can start talking about how some other technologies build on this. And I'll talk about three, but there are others. Internet of Things, I'll talk a little bit more about this. Cloud RAN, and 5G cellular, the technology that's coming after LTE. And then I had a lot of fun making this animation. So a key concept, and we'll go through it as on subsequent slides, is not only do these build on the basis, but they're actually linked with each other. So again, the key theme here is that we should not be viewing technologies as individual pieces, but rather part of a bigger whole. So here's IoT, and we can use this principally to highlight redistributed intelligence. So in the past, and even today, you hear a lot of people talk in a very thing-centric view. Internet of Things, they talk all about all these neat things, from the sensor in your oil pipeline, in a oil pipeline, or a sensor in your refrigerator telling you, the smart refrigerator. I think we've heard that story for the last 20 years. Or the thing on your wrist that's measuring your health statistics, and there's some gateway that aggregates it, and then the data goes off to the cloud, magic happens, and then somehow it's presented back to you, or some decision is sent back to the things. I mean, it's an okay view of the world, but it's very thing-centric, and it's missing a lot of what makes more sense in this evolved network paradigm. So the first thing we can do in this evolved network paradigm is we need to recognize there are multiple parts in this network. It isn't just sort of local stuff and far away stuff, but they're intermediate steps. And we can take intelligence and we can push it down and do the analysis on the data being thrown off by the things where it makes the most sense, depending on the context of what's being processed, the context of the decision that needs to be made, and how much bandwidth we have, kind of north of where that data is being generated. And once we have intelligence at these different places, and we're looking at kind of this bigger picture network with a lot of different nodes, how do we control it? Well, SDN provides an excellent framework for providing that control. So there could be an SDN controller in the cloud that says, oh, some things need to talk to adjacent things. So Mr. Gateway, if you see this type of traffic, you make sure it goes on this virtual network that you've set up under my command to route the traffic from here to here. So that would be one example. And then other traffic, sure, send it up here. Oh, there's a problem. The network went down. What's the failover path? Well, your controller can say, all right, here's the new path to where you need to send the data. And then as we have this redistributed intelligence, just as a general concept, as doing some kind of processing or analysis or networking function, why don't we virtualize that, put that in a virtual network, take that virtual network function, put it inside each of these redistributed intelligence points, and maybe even move virtual machines, up and down or left and right, depending on, what's the load, what processing node has the most capacity, or going back to this idea of context of data, what node has the proper context for looking at the data. So again, here, an example of IoT tying all three of these evolved network concepts together. And the one I really want to leave you, if you have to try to remember one to associate it with it, is this redistributed intelligence, putting intelligence throughout the network where the context makes the most sense. Now we talk about Cloud RAN for a moment. Today, our cellular network is based on macro cells. You can look out the window and you'll see there'll be a tall tower with antennas on it and a little shed next to it that houses the base station. This, and then these traffic is hauled back to this evolved packet core that does a lot of the packet processing and networking functions that get your voice and data from your handset. Kind of, we know how it goes from the handset to the space station, but then how do we get it to the internet? Well, that's what the evolved packet core helps with. There's an alternative approach that's not necessarily going to replace, but is going to supplement this architecture in certain applications, is Cloud RAN. So what we do there is we just have radio heads. So we take out a lot of the intelligence that's in that Radio Shack, and we move some layer 2 functions onto a virtual platform, virtualize them and put them on a multi-core platform. Layer 1 functions, a little bit harder to virtualize, real-time requirements, but we can still pool them and draw on them as a collective resource. And we can virtualize our EPC, the embedded packet core, and then we can control a lot of how the traffic is steered and managed using our SDN controller. So again, we're talking about redistributing intelligence. We're taking it out of the macro base station, moving it up to the cloud. We're talking about virtualizing and then using SDN. So again, an example of how the evolved network can be used, there's principles used and applied in a totally different scenario than IoT. So 5G is interesting. Not only does it draw on this concept of the evolved network, but it also interlinks with the prior two concepts, IoT and Cloud RAN. So in 5G, the objective is to support 10 to 1,000 times more users, where user in network talk doesn't mean a person, but it means something at the other end of the radio connection, and deliver 10 to 100 times the bandwidth. Peak bandwidth, not necessarily 100 times to your smart refrigerator, but maybe 100 times to you, the user. So we've got these billions of IoT nodes. We have these smartphones. So this is a new thing, and this is really generating a lot of the additional network users. We have smartphones and tablets, which we're familiar with. Augmented reality, we have Google Glass and so forth. So imagine this future where you're walking around, you see something, your glasses see something, it can recognize what you're looking at, it can annotate, it can communicate to you what it's looking at. That's going to require a lot of processing, both locally and far away. And then two-way 4K video, where 4K is the thing after HD. So higher resolution and therefore more bandwidth. These are some of the things that are driving the bandwidth and the additional users. So with SDN, this controls the access nodes. So for example, it could be applied to facilitate handoff between the 5G network and the Wi-Fi. It could also control the path to the internet. So today, for example, everything goes up to the EPC and then goes out to the internet. Well, if you're on your smartphone, why does that data have to go through the EPC, which is a very expensive resource that the service provider operates? Why doesn't it, once it goes to the macro cell, why don't we just shunt it off to the internet directly? And that's something SDN can facilitate without violating the principles and the policies of the service provider, the carrier. So in terms of NFV, the example here is just simply that goes back to the Cloud RAN example, because we expect Cloud RAN to be an implementation that is used more fully in 5G. And then redistributed intelligence, again, talking about these principles here of the moving some things up to the cloud. For IoT, we move some things down to these cells, whether, like your macro cell, your small cell can have intelligence next to it to do the processing for the Internet of Things. So changing gears, how do multi-core processors have to change? Well, first, they have to be easy to use. Second, they have to be scalable. And third, they have to be well supported by software. So let's talk briefly about easy to use. This was the subject and the key graphic from the multicore DevCon talk of a year ago. And the idea here is us processor companies, we were in this megahertz race for a long time, and then it became ever harder to achieve higher and higher clock rates. So we turned to increasing core count. And we can do that, and we can keep doing that for a long time. But it doesn't really improve the situation altogether. We need to do something more because we can add features, we can add cores, but if no one can use them, if no one is using them, then we're really not accomplishing anything. So therefore, usability is really the next wave, the next challenge for our industry, and someplace where Freescale is taking the lead in terms of addressing it. So aspects of easy to use is we need to have an open instruction set. And open, people talk about open and meaning a lot of different things, and a lot of different people use that word. But in my mind, open is really multi-vendor. So not only can you use it open in that sense, because basically everything's open if that's your definition, but it's openly available from different suppliers. And the customer can choose the best one. Other things you can do to make things easier to use is peripherals and accelerators are objects. They are not, they become abstract. They become something that software can readily, you can write code that readily uses them without having to understand how they work to make them work. And then if you're going to put something like a packet engine or anything else that's very flexible and very, if you're going to create something like a packet engine that you want to be flexible and programmable, it has to be programmable in a way that's very simple. And one aspect of the programmability is being C-programmable, and C-programmable in a very much the general sense. C-programmable like you program a computer, where you don't really think much about the underlying hardware. Even something as simple as memory, you just go ahead, write your code, and everything seems familiar, as if it's in that computing paradigm. And then things like management and configuration are abstracted. Again, taking away the user having to know what are the specifics of the hardware to make it work. They can just make it work because they have this more abstract presentation of the capabilities of the multi-core processor. And it also has to be scalable. We have to be able to go from, this itty-bitty IoT gateway, maybe something that could fit in the palm of your hand, up to these large systems that, are rows and rows of racks filled with lots of different equipment. And again, scalability, it's not the old version of scalability where you just throw more megahertz at the problem or throw more cores at the problem. It's scalability in the sense of, is there a common platform? Is there a common way of understanding everything that the multi-core processor does? Because it's really an SoC. Can we approach it the same way when we're talking about an itty-bitty one to a really, really big one? And then, these chips that we make at Freescale, there'd be nothing more than paperweights if no one could run software on them. Software is essential to unlocking the performance. And what we're finding is a void is opening up in the value chain. So if you look, traditionally Freescale has been here with our peers and would provide a thin veneer of software on top, and then OEMs would design the system, including the system software and the system hardware and the applications that ran on top, and then they would sell their equipment to somebody who delivered services. Well, they're moving up the chain to provide services, and as they do that, they're leaving a void down here and leaving part of this open, and this area is also becoming increasingly hard for third parties to fill because these, again, these multi-core processors are really SoCs and very complex, and unless there is abstraction both in the hardware, like I was just talking about, as well as in the software, there's really no way to scale across multiple vendors if you're providing that thin layer of software. So what the processor companies are doing and need to do is move up the market, filling this void, filling the black hole that's opening up here, and providing more and more building blocks at a higher level, such that the companies creating the applications don't have to reinvent the wheel or the many different wheels and gears that are the basis of the application. So part of this is creating vendor neutral APIs. So when you write your application, even if you're targeting code, you don't have to target a specific vendor or a specific processor. But that processor vendor has to provide turnkey optimized code so that you get the most performance and best utilization of the features of the hardware. The vendor's going to have to support Linux. This has become the standard operating system, the kind of the baseline that customers are using. And they're going to need some help in some cases to either fully utilize the processor, or to supplement their own development resources, or to implement something where the supplier of the multi-core technology has gained experience and done a lot of thinking in the process of developing his hardware. He can help the OEM, the system designer, out by providing services based on that expertise to help them develop their applications. So how is Freescale enabling this vision? Well, we have our multi-core, Core IQ communications processors, our layerscape architecture we talk about, very much focused on addressing the ease of use challenges. And it is really designed for this evolved network. If you look at it in totality, it has virtualization for NFV. It's scalable, so wherever you need intelligence in your network, you can find a processor that's the right fit. And it also has these capabilities to handle all the bizarre encapsulations and under definition software that's part of SDN. And we also have the industry's broadest portfolio. Today we have communications processors from 1 to 24 cores. We have wireless processors from femtocells, base stations you can hold in your hand, to highly sophisticated, high-performance processors that are actually being used in Cloud RAN deployments today to perform those L1 functions and other real-time functions. And then we have IoT components, everything from what you need to do as an IoT company, from the sensor at that end node all the way up to the technology that you'd find in the cloud, in the data center. And then we're investing heavily in software and standards. In the digital networking organization alone, we have 700 software engineers. We provide commercial software and services. We are a leader in the dominant open source SDN technology, OpenFlow, and certainly a leader amongst the multi-core processor suppliers in terms of having latest generation compatible plugfest tested software. And we engage with operators and OEMs on network functions virtualization. So, starting with this evolved network, we can build on it and we can create something great. I've highlighted 3 functions here, or 3 things we can build: IoT, 5G, and Cloud RAN. I've shown how they interlock with each other, as well as the underlying technologies that are the evolved network. But the same can be done for a lot of these other technologies that we hear about on an almost daily basis, whether it's telematics, BYOD, or big data. And the question that our customers should ask, and our prospective customers should ask, is, can your multi-core supplier do this? Because Freescale can. Well, thank you very much for joining today, and save me a cookie.